Good day to all of you. Today we shall continue the design of the controller for DC-DC converters. In the last class, we tried the design with the trial and error approach, also called the Ziegler-Nichols method, and we saw how we go about tuning the PID parameters, PI parameters to match a performance specification. In this class today, we shall discuss a more formal approach called the root locus technique. What has been popular is both the root locus technique and the method by the Bode plots. Bode plots have also been very popular in the design of the controllers. However, we shall be adopting only the root locus technique here. The reason being that in many converters you have zeros on the right half of the S-plane, like the boost converter for example, which has 0 on the right of the S-plane, the small signal model. Because of that, the Bode plot will not work. The Bode plot will work for non-minimum phase systems only. Therefore, we shall take the root locus approach, which is a more general procedure, whether it be for non-minimum phase systems or any other systems, as long as you have linear time invariant systems. So, that is why we are going to focus on the root locus method. So, more generic approach. It has not been so popular before the advent of the computers, because it is very computation intensive, and then doing hand calculation is a very problematic situation. Therefore, the Bode plot approach was more preferred. However, after the advent of the computers, the computation and all other bulwark was shifted over to the computers, and finding the root loci was not a very difficult task. And therefore, root locus started gaining in popularity, and today it is a very popular method to design controllers. Now, if you take a general control block diagram, as I am indicating here, let us take a general controller which has a reference, a feedback, a controller, and a plant, feedback with feedback sensing, signal conditioning, in this fashion. Okay, let us say this is our general control system block diagram. Now, let us say the controller has a transfer function which is split into two parts. Now, I will split the controller into two parts. One part is just simply the gain, and I will call it as K. The other part gives you the structure of the controller, pole 0 structure of the controller, and let me call that as GC. This is the gain part, and this is the pole 0 structure. Likewise, the plant has a transfer function, and let us call that one as NP, GP. The feedback portion has a transfer function, and let us call that one as H. Now, the closed loop transfer function is given by K GC GP by 1 plus K GC GP H. So, this is the closed loop transfer function, and after our controller design, what we are interested is in the location of the roots of this. This basically gives the poles of the closed loop transfer function. The roots of this will give the location of the closed loop poles. So, therefore, we say that 1 plus K GC plant transfer function H is the characteristic equation. The roots of this will give you the closed loop pole location. So, the idea here is that, let us say that you are given the flexibility to choose the closed loop pole location. So, this is the S plane. We choose the closed loop pole locations on the left of the S plane, stable according to a particular performance criteria, look at the transfer step response, and then match it to the performance requirements. So, the closed loop pole location is decided by the designer, and then that is used to calculate the unknowns in this equation. The unknowns in this equation is this. This is known, the structure of the controller is known, we are the designer is giving the structure, location of poles and zeros, the model of the plant is known, the model of the feedback portion of the circuit is known. So, the only unknown would be K, and if we know the roots, which is the closed loop pole location, which let us say the designer proposes and then says, okay, let me place the closed loop poles at these points, and then use those to calculate and find out K. Okay, so, that is the principle. It is basically like working back. You decide, okay, this should be the final ultimate closed loop pole location, and then find out what is the value of gains K, which will meet the spec. If it does not meet your performance specification, change this controller structure, repeat the process, and then try to find K. Okay, so, that is the principle. Now, if you look at this 1 plus k GC controller plant H equal to 0. What is the condition that satisfies this equation, which will give the roots? K GC GP H should be equal to minus 1, or the magnitude of K GC GP H should be equal to 1, and the angle K GC GP H should be pi 180 degrees or in a more general terms, you could have 2n plus 1 pi. Now, these two constraints, if they are matched, then all those points in the S plane for a given GP, for a given H, for a given GC, varying k from 0 to infinity, if we plot all the points that satisfy these two constraints, then we probably will get a sequence of points, so on, something like that sequence, many such points. Now, the locus of all these points is called the root locus. This may be at k is equal to 0, k is equal to 1, so on up to k tending to infinity for each. So, that is basically the principle. Now, let us look at just a simple closed loop system kg by 1 plus kg, where H is equal to 1, GC is equal to 1. Okay. When you take such a condition, okay, 1 plus kg is equal to 0. Now, this has our rewriting kg is equal to minus 1, k into numerator polynomial by denominator polynomial. These are all functions in S is equal to minus 1. Now, if you look at the numerator polynomial of G, this is zeros of G. These are poles of G. So, at values of S, which are tending to the poles of G, you will find that this portion tends to 0 and the whole G tends to an infinite value. So, if G tends to an infinite value, K should tend to 0. So, if I write this as, I will put it in the next page, K G minus 1. If G tends to infinity, then K should tend to 0 to satisfy this condition. So, at open loop pole points, at open loop pole points of G, K is 0. Now, for the same Kg equals minus 1, at the open loop zeros. So, as at values of S that are matching with the zeros, G becomes 0. G becomes 0. So, K has to go towards infinity to satisfy these conditions. Therefore, at open loop 0 points of G, K is an infinite value. So, therefore, we can say a general statement valid for root locus: as K is varied from zero to infinity, the root locus starts from open loop pole K equal to 0 and ends on open loop 0, K infinite. So, this is a general statement that we can make for root locus method. Anyway, you need not worry, this is a concept that you should keep in mind when you are trying to adjust the place the poles. The computer does the job of calculating all the roots, solving these equations, specifically this equation, and plotting to you the root loci of the system. So, if it is a third order system, then you will have 3 root loci. If it is a second order system, you will have 2 root loci. First order system, 1 root loci. So, for every order, there is a pole, open loop pole, and then if you have an open loop pole, then a root loci starts from that open loop pole and then ends at open loop 0. If the 0 is finite or the 0 is not there, then it will end at infinity. It will asymptotically tend to an infinite point at infinity, thinking that equivalently saying that 0 is at infinity. Okay, so now coming back to our problem, which is the DC-DC converter. DC-DC converter. Let us have a reference, V0 reference, a comparator, goes through a PI controller, and this goes, let us say, to a boost converter. This time we will take a boost converter. Yesterday we took a buck converter, probably to keep things different. Let us say you have a boost converter like this. This is V0, this is Vn. Okay. So, let us have a pulse width modulator, which will drive this switch. This is your plant, let us say. Or we could include the PWM also into the plant. Now, if we could probably do that, include the PWM also into the plant. Now, this controller, PI controller, can be written as, you have an integrator S, you have a 0, okay, to account for the proportional part, and then you have one consolidated gain. So, this is the split for the PI controller, and the output of it passes through H, and so this is how the system looks like. And importantly, I want to bring your attention to this PI controller transfer function. So, you have the I portion and the P portion, you have a consolidated gain. This is positioned by the designer, this is the control structure, how many zeros and poles and where they are located, and this is the gain. So, this would be our GC, this would be GP, and you have the H. Now, let us apply the root locus method to design what? We have to design this. So, the moment we decide that it is a PI structure, you have 1 0 and 1 pole to place on the S plane. So, if you take the S plane, the controller GC is K is separated out, S plus A by S. At S is equal to 0, you have a pole, and at S is equal to minus A, you have a 0. So, this is the positioning of the pole and 0 for the PI controller, and K is a variable parameter that is varied for the whole locus. So, the steps is, we will go to the computer, we will open an M file text editor. You can either perform this iterative action by running a program either in MATLAB or Octave. Octave is open source, compatible with MATLAB language. So, I will be using here Octave for running the scripts. So, the script should be partitioned in the following manner. First, we need the model. Then, after we have the model of the plant, that is GP, which will give you a numerator polynomial and denominator polynomial. Decide on the control structure, which will give you the numerator polynomial of the controller and the denominator polynomial of the controller. And then define feedback transfer function of the sensor, which will give you H, the numerator polynomial of H and the denominator polynomial of H. We need to split it that way. Then after that, we try to obtain K, GC, GP, H. This is the loop transfer function. So, loop transfer function is nothing but k into n g c by d g c in terms of polynomials, n g by d g, n h by d h. So, numerator and denominator polynomials of g c, numerator and denominator polynomials of g p, numerator and denominator polynomials of h. Then using k as the parameter, varying k from 0 to infinity, we try to obtain the root loci. So, the root locus, then we try to plot the root locus or loci of the above transfer function. Then we choose a closed loop point, choose a closed loop closed loop point set. Why I mean set is that if it is a first order system, you are choosing one closed loop point. If it is a second order system, you need to have two closed loop pole points, pole points. But if you choose on any one locus of the root loci, for the corresponding k, the other points are automatically chosen on all the other loci. Okay. Then do a step response test. Check the step response whether it is satisfactory or not. If it is satisfactory, then you can stop here and that would be the value of k. If it is not satisfactory, again you can go and choose this. Even after many iteration, you do not get a satisfactory is one. You can go back here to the point 3 to set GC structure and then follow the procedure again. So, this way you try to obtain the optimal, not optimal, reasonably good specific performance matching, and that value of k which you have chosen would be the one that you will plug in into the simulation. So, these steps we will try to follow in MATLAB or Octave and try to see how it works. Now, let me go over and switch over to the computer which will do the simulation. So, I have here a blank screen, it is a text editor, and let me go through the process of writing the script. So, this can be a M file and we shall say this is a script file to demonstrate the root locus technique of controller design. Now, the model of the plant. Now, take an example model. This is not the example model of a DC-DC converter, but let us say some arbitrary example. Okay. Now, let us say define Ng equals 1. This means that we are having the numerator polynomial only s to the power of 0, okay, no zeros. Now, dg, the denominator polynomial, let us say if you define as 1, 0.5, then it implies the denominator polynomial is having s 1 into s plus 0.5 into s to the power of 0, that is s plus 0.5. So, each coefficient raised to the power of, so this is 0.5 s to the power of 0, 1 into s to the power of 1, and so on, if you can add any more. So, let us take such a simple plant, first order plant, and then see how we go about doing. So, after that we define the controller structure. So, NGC, the numerator polynomial of the controller, let us say is 1, again no 0, and denominator polynomial is 1, 0, which means you have a pole at s equal to 0, that is integrator only. Okay. Then define the transfer function h. This NH, right now we will keep it simple, 1 and 1, no poles, no zeros, just 1. Now, let us say the loop transfer function which is GC into GP into H. So, this is GP, this is GC. So, the numerator polynomial, the loop transfer function is convolution of NG and NH. The denominator polynomial of the loop transfer function is convolution, multiplication of the polynomials, straightforward polynomial multiplication, and we get that. Fine. So, this is the, if you would like to see what you have got till this point, just copy. Let us first save this document. We will save it in some place. I will call it as test. Okay. So, you can copy this, go to Octave, okay, and paste that in Octave to see what you get. So, this is executed, NL is 1, DL is, so this is s to the power of 0, s to the power of 1, s to the power of 2. So, the closed loop transfer function is second order, one order being contributed by ENGDG, another order contributed by GC. H does not contribute any order because no poles on 0. So, you have a second order system there. Now, let us look at the closed loop. Let us look at the root locus. So, let us say you have k and p equals function rloc find the. So, if you give rloc find the loop transfer function numerator polynomial and the denominator polynomial, it will plot the root locus and allow you to click a point on that. Okay. So, let us say I will save that, and then I will copy and then go back to Octave, and let us say we paste that. So, it will present to you the root locus plot. See, this is the real axis of the S plane, and this is the omega axis or the imaginary axis of the S plane. The blue lines are the root loci. There is one pole here. Let me see if I can maximize this. Yes. Observe that there is one pole here. This is the pole that has been contributed by the designer placing the controller at s is equal to 0. That is, he has placed an integrator, used an integrator structure. So, there is one s is equal to 0, open loop pole GC GP. There is another pole here at 0.5, s is equal to minus 0.5, okay, because of the plant. Now, these two are the root loci coming in here. Now, you could choose, you could choose a point on this. It will indicate these are the points chosen, the closed loop points chosen, and the value of k at these points is 0.076778, and the closed loop pole locations are these two. So, that is what it would indicate, and you could use this value of k, let us say, and get the closed loop system with k, which is k GC GP H by 1 plus k GC GP. Now, for that, to get the closed loop system, so let us say the closed loop numerator polynomial, denominator polynomial is given by feedback the into k. So, k numerator k into NG that is GC numerator polynomial of GC and GP, then multiplication of the denominator polynomials, then specify the feedback polynomial. So, that would give you the closed loop transfer function. After you get the closed loop transfer function, you could do a step response check using step, convert it into a system NC DC, which is the, so this is the step response check. So, if I take these two, copy and go to Octave, and Octave, let me paste them. So, this will make the closed loop transfer function, then the step response of the closed loop transfer function. When you execute it, you will get the figure, which is the step response. You have with respect to time and the amplitude for a unit step, this is the response. Now, this can be made iterative. Okay. So, let us make it iterative such that you can keep repeating. Okay. So, what we do, we try to put it into a loop. Okay. So, this same function, what I the portion of root locus, then the portion of one with feedback and the step calculating the step response can be put within a while loop, and you can ask a query 0 to quit or 1 to continue. Okay. So, this would tell us, okay, let me for now remove some of these things. Okay. So, I have saved it into another file called Locus design. Now, yeah, let me call Locus design. So, this is the first call. It will tell you that this is the root locus. Let me choose a point. Then after the choice of the point, the step closed loop function is calculated, the step response is plotted. You see a step response of this nature. Now, you could take, let us say, continue. You will be presented again with the root locus, and let us say we choose some other closed loop point. We choose some other closed loop point, and you see that the k value is lesser, and see the k value in the previous iteration was 0.334. Now, in the present iteration, it is 0.07, much lesser, and the overshoots have been reduced. So on, you can keep iterating, choosing different closed loop points till you get the response according to our performance specification. So, that is the then you can put 0 and come out. Okay. Now, the thing is that let us try it on DC-DC converter. Now, for that we need to modify a bit this root locus design point. This should become the model of the converter that you would want to use. Now, let us say we want to use the model of a boost converter for now. Okay. So, I have prepared here the model of the boost converter in this file here. Let me open this script file. Okay. So, the boost converter, these are the parameters: Vg 15 volts, duty cycle of 0.4, inductance 2 millihenry, capacitance 10 microfarad, load resistance of 100 ohms, and switching period of 50 microseconds or 20 kilohertz switching. Okay. The steady state model, we have gone through that, we have developed that before. The A matrix is 2 by 2, you have the B matrix. The B matrix is 2 by 3, meaning there are 3 possible control inputs, which is, it could be the input V in itself, or Iz the load, or D the duty cycle. We are of course bothered about control with respect to D. Okay. And we have the steady state model and then the small signal model AC. Now, the small signal model is the one that we will be using for control. Okay. And after substituting these values, it will execute, and then you convert the state space model to transfer function model. This is zero pole display, and this is the transfer function model. Let us just take, so this last statement says SS to TF, state space to transfer function of AC, and B matrix, you are taking only that column which represents the duty cycle input column, then the C matrix and the D matrix, which is true. This will give you NG and DG. Now, this NG, DG, you use it in the root locus design. So, what we could do, let us disable this so that NG, DG is disabled here, and we execute this boost model, and from the workspace we will clear all. Let us go to boost model, we will execute that. So, you see the steady state output, the transfer function, this is the transfer function of the boost converter, small signal, with respect to Vg input, with respect to the load, the second one, and then with respect to duty cycle. Okay. And it gives you the Ng and Dg, the numerator polynomial Ng and the denominator polynomial Dg of the transfer function with respect to the duty cycle input, that is this. So, that is what you have here as Ng and Dg. Now, you could run the root locus design script such that it takes this Ng and Dg and applies a integrator, just only a plain integrator, because in the root locus we had just kept a plain integrator, if you remember. Remember that in the, we have right now the control structure is 1 by S, which is an integrator. Of course, you can make the control structure into P, Pi, PID later on, but the concept is to propose that, and then we get a root locus plot generated by the loc-find tool, and we need to specify closed loop location. observe that this is the 0, this is the right of the S-plane. If I click anywhere on the right of the S-plane, which means you are trying to choose a closed loop on the right of the S-plane, you will get step response which is unstable, kind of 0 and then starts growing. Okay. So, you have to now, as this is pretty well compressed, let me zoom it towards this point here. Now, you see this is the 0 and I have to choose in the left of this plane somewhere here. Okay. Well, let me now make the choice at around this. Automatically other 3 are chosen and then you have a step response which is something like this for this value of k. These are the closed loop point locations. So, for this value of k, which is used as the closed loop as the controller gain, and then k into GC into GP divided by 1 plus k into GC into GP into H, that closed loop transfer function has a step response like this. So, you can keep iterating and try to get better and better step responses and then design the value of k. Once the value of k is designed, then your controller is defined, everything in the controller gets defined. You can then add, you can now add as homework to this. You can add, we had right now given 1 by s. You can now make it s plus a by s, which means now you have put proportional plus integrator, which is 1 plus a by s. This is a proportional plus integrator. Add these and then try it out and then choose the gains accordingly. Then plug that into the simulation. We will just try a simulation of the boost converter in the next class and then go on to the next topic. Okay. Thank you for now.